Now you might wonder, what would happen if we tried to optimize the number of values we use in the fast and slow SMA? In the next part of this lecture, that's exactly what we're going to do. The basic idea is we're going to split the data into a train set and a test set. We're going to use the train set to select the fast SMA and the slow SMA, and then we'll evaluate it on both the train and test set. In other words, we will choose the fast SMA and slow SMA that give us the best return on the train set only. In machine learning parlance, you might think of the test set as a validation set. Okay, so this function takes in three arguments: the full data frame of close prices, the fast parameter, and the slow parameter. Inside the function, we're going to again declare isInvested as a global variable. Next, we're going to calculate the fast SMA and the slow SMA using the values of fast and slow that we passed in. Next, we're going to repeat all the steps we did above. First, we find where fast SMA is bigger than slow SMA. We assign either 1 or 0 based on the result. Next, we assign the prev signal column by shifting the signal column by 1. Next, we set the buy and sell commands using the same logic we had before. Notice how we do all that work before we split the data into train and test. So why do we do it this way? Remember that when we calculate the SMA, the first few values will be missing until we have enough values to actually calculate the SMA. So if you want SMA 10, then for example, the third value is going to be missing because you can't calculate SMA 10 from only 3 values. Now, the result of this is that in the whole data frame, only the first few values are missing. That means only the train set has missing values, but not the test set. If we had split the data into train and test first, then you would have missing values in the test set as well. But that doesn't really make sense, since in the real world, you would have historical data when you begin testing your strategy. Anyway, if that doesn't make sense to you, you can safely ignore what I'm saying. I only mention this since it's a thought that I had when I was creating the script. Basically, the function would take in only the train set or only the test set and apply the algorithm on each of them individually. This function, on the other hand, takes in the whole data frame and splits it into train and test, and then gives you back both the train return and the test return together. Again, if that doesn't make sense to you, it's not necessary to understand. Alright, so next, we're going to assign the isInvested column. Since we always start out not invested, we have to assign the global variable isInvested to false. Next, we call train.apply. Next, we multiply isInvested by the log return. Next, we do the same process on the test set. Finally, we return both the train score and the test score. Now you'll notice I'm doing something weird here, which is that I'm not including the last value in the sum. This won't make sense right now, but it will when we look at the reinforcement learning version of this script. Intuitively, you can just think of the test set. The test set has no final return because we shifted them earlier, if you recall. Therefore, on the test set, this actually has no effect, but on the train set, it does. So another reason is just for uniformity. This has more to do with the fact that there are limitations of working with data frames and not having data that goes on forever. So this is just some housekeeping we're going to do so that the results we get now are in line with what we will get later. Okay, so next, we're going to test that our function works. We'll use the same fast and slow parameters that we used earlier so that we can sanity check the result. Okay, so we get about 0.21 and 0.09, which sum up to 30%, so that makes sense. Next, we're going to do a grid search to find the best fast and slow values. We'll start by setting best fast and best slow to none. We'll initialize best score to -infinity so that any score we get can beat it. Next, we loop through the fast and slow values to try. Note that these are pretty arbitrary. They're kind of like hyper parameters. Feel free to test your own values if you don't like these. Again, I'm just showing you the method, not telling you what the best values are. Okay, so inside the loop, we're going to call our trend following function with the current values of fast and slow. Note that we ignore the second return value because we will only use the train score to evaluate the parameters. If the train score is greater than the current best score, then we save the score along with the current values of fast and slow. Finally, when this loop is complete, we call our function one last time on the values of best fast and best slow that we found. Okay, so let's run this. Okay, so we see that for the train score, we get only 43%, and for the test score, we get only 9%. Of course, these values only make sense in the context of the baseline, which is buy and hold. So next, let's split the data into train and test and make copies for later. Next, we'll sum the log return column for the train set. Again, we sum only to the second last value. So the result is about 60%. Again, buy and hold wins. Next, let's look at the test set. Again, summing to only the second last value has no effect since the last value is actually missing. And again, buy and hold wins. We get about 19%. Now, it might be worth checking the Sharpe ratio as well, just to see if our strategy has any redeeming qualities. So in this block, we're going to print the Sharpe ratio of the algo log return, as well as the log return. We see that the Sharpe ratio of the algorithm is slightly higher, so not being invested does at least reduce variance. Next, let's do the same thing for the test set. Unfortunately for the test set, buy and hold wins again. Okay, so the last thing we're going to do in the script is plot our wealth over time. Since we worked with log returns and not regular returns, we have to do this carefully. First, we're going to calculate the cumulative log return for each time step by calling the cumsum function. We're also going to shift this forwards since, as you recall, the returns are currently shifted backwards. Next, we're going to calculate our cumulative wealth on each time step. This is equal to the initial price multiplied by the exponential of the cumulative log return. Now, you might ask, how do we get this? Okay, let's suppose we want to calculate the log price at time t from the log price at time 0. We find that P1 is equal to P0 plus R1, P2 is equal to P1 plus R2, but that is equal to P0 plus R1 plus R2. We can keep repeating this pattern until we find that P at time t is equal to P at time 0 plus the sum of the log returns up to time t. Of course, if we just take the exponential of both sides, we recover the price at time t, the price at time 0, and the exponential of the sum of log returns. Okay, and the last step is to simply call the plot function on the relevant columns. So what do we get? Well, it may be a bit hard to see, but you're encouraged to zoom in on your own computer. Basically, look for all the areas where we have a straight line on our cumulative wealth. These should start at the sell points and end at the buy points. Unfortunately, it seems like our algorithm reacts too slowly, so we end up investing after the stock rises and selling after the stock drops. One fact we know is that the exponential moving average doesn't lag as much as the simple moving average, so you may want to give that a try as well.